This is a video presentation by Lawrence Finzel concerning his findings of the Davis-Besse nuclear power station boric acid wastage incident. In 2001, the Nuclear Regulatory Commission issued a bulletin concerning primary water stress corrosion cracking leading to boric acid wastage of reactor pressure vessel components. On February 16th, the Davis-Besse nuclear power station began a routine refueling operation. During this operation, they intended to inspect the CRDM reactor pressure vessel head penetrations for the presence of primary water stress corrosion cracking. On March 6th, during repair operations on the number 3 CRDM nozzle, malfunctions in the equipment caused the Davis-Besse nuclear power station to remove repair equipment. Upon the removal of the equipment, the number 3 CRDM nozzle fell downhill, resting against another CRDM nozzle. During visual inspections the next day, it was determined that a large area of boric acid wastage had removed all of the structural material that was responsible to hold up the CRDM nozzle. This was caused by boric acid crevice corrosion cracking and boric acid wastage. Primary water stress corrosion cracking of the number 3 CRDM nozzle allowed for borated water to reach the low alloy steel present in the reactor pressure vessel head. Primary water stress corrosion cracking is a phenomenon known in alloy 600. It was discovered in 1969 after the design of the Davis-Besse nuclear power station was complete. Primary water stress corrosion cracking requires 3 components for it to occur: stress residual to the metal, environmental stress, and a susceptible material. The easiest of these to mitigate is the tensile stress present from manufacturing of alloy 600 components. A process known as peening can be used in the mitigation of this stress. Peening produces high pressure shock waves by using either water jets, shot, or lasers, which produces a compressive stress on the surface of alloy 600 components. This stress reduces the tensile stress remaining from cold working or forging of alloy 600 components. By reducing this stress, alloy 600 components are less susceptible to primary water stress corrosion cracking. Peening has been shown to be effective in new components and in components that have already been installed in reactors. It is even effective at reducing crack mitigation after it has begun. Boric acid is a weak acid that is used in pressurized water reactors as a poison. This acid allows the reactor to be loaded with a greater fuel load while maintaining a flat power distribution, allowing for longer operations between refueling. Refueling forces the reactor to be shut down, costing the licensee time and money. The presence of boric acid strips the protective corrosion layer from low alloy steel. This is due to the hydrogen ions which interact with the iron ions and pull them away from the surface. This phenomenon produces high corrosion rates. Laboratory tests have shown that corrosion rates can reach levels of 6 inches per year. Boric acid wastage is a major concern for the safety of reactor components. New designs have used materials that are not susceptible to boric to primary water stress corrosion cracking, such as alloy 690, to prevent this phenomenon.